because we're going to measure OS. What happens with the sine of 2 alpha? The sine of 90 degrees is 1.0000. But what would be the sine of 88 degrees? That is the value that I cannot exclude if I'm off by 1 degree. And that value is 0.9994. That is so close to 1 that it is only off by 0.6%. 0.06%. And that is so low compared to 5%, forget it. Forget the error in alpha. We can completely forget it. There's a reason for that. When alpha is 45 degrees, then 2 alpha is 90 degrees. And the sine curve goes like this at 90 degrees. It's almost flat here. So even if you're off in angle by a little bit, you're still very close to 1. That's the reason. So all we have to worry about is the uncertainty in V0 squared. And so now comes my big prediction. I'm going to make a prediction now. For 45 degrees, OS equals V0 squared. We have that is 60.2. And we have the sine of 2 alpha is 1, and we divide by 9.8. That is 6.14 meters. With an uncertainty of 5%, right? Because that's the uncertainty in V0 squared. And so that is an uncertainty of 30 centimeters, actually 31 centimeters. This is my prediction. For an angle of 45 degrees. This will only hold if there is no air drag, or if the air drag is negligible. And of course, equally important, that spring gun, when the ball comes out, that the velocity square is indeed within the range that we have assumed, and that it doesn't have bad days and good days. There's no way I can check that anymore. All right? So we're going to mark the point 614. This is 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter, 6.14. 14 centimeters. Oh my God, it's all the way here. And then I allow for an error of about 30 centimeters. Did I do that right? That is correct. 45 degrees, a 30 centimeter uncertainty. That is all the way up to here. And then the next one, roughly 30 centimeters. So that's where, if our calculations make sense, that's where the ball should hit. Now I would like you to come here, if you don't mind, and stand here. And the moment that that ball hits, point your finger at it. Don't do it before I shoot, but just after I shoot. And then we'll hope for the best. Yeah? Okay. You're not nervous, right? What happened with that ball that I had? Did I put it in my pocket? Oh, it's here. Thank you. So I'm going to set it now to the best I can at 45 degrees. And so I can never shoot it any further. This is the angle, this is the maximum possible distance. You ready? You are? Don't look at me, look there. It goes fast. 3, 2, 1, 0. Put your finger there. Isn't that fantastic? Isn't that amazing? Do you see now how important it is that you have uncertainties in your measurement? In high school you would have said it has to hit there. Bull, man. It has an error. And the error has to be taken into account. Where's my ball, by the way? Boy. Oh, I have it. Ooh, here. Ah. Okay. You can sit down now. You did great. It worked just because you were there. So now, I wonder what happens if I fire the ball at 30 degrees. Well, if I do it at 30 degrees, then my V0 square is the same. I don't have to worry about that, I hope. However, I cannot be certain about the angle to better than 1 degree. So you will say, well, come on now. Don't be decadent. I mean, here we had an error of only 0.06% because of this 1 degree, possible 1 degree offset. Let's just ignore this error too. That is risky. That is risky now. Because the sine of 60 degrees, that's what you deal with. The sine of 60 degrees, I think, is 0.866. That's right. But the sine of 58 degrees, which is possible if I'm 1 degree under, is 0.848. And that is substantially lower. And therefore, I must allow for an uncertainty in the sign of the angle by roughly, oh, maybe something like 17 or 18 units. 0.0, what is this difference? 0.018. If you want to check what the sine of 62 degrees is, you will see that that is about this much higher than this. So we must allow for this error. And that is an error which is by no means negligible anymore. There's no point here. That is an error which is 18 divided by 866. That is a 2% error. So now we're dealing all of a sudden with a 2% error in the sine of 2 alpha, even though there's only a 1 degree uncertainty in the angle. And the reason is that a sine curve is like so. So a small angle change here makes no difference, but a small angle change here makes a lot of difference. And that's the reason. And you can see that it is the slope of the sine curve that gives you a much larger error if you are off by a teeny-weeny little bit. So now we're ready to make a prediction. So here comes the prediction. OS, now for 30 degrees. So I have to go through V0 squared, I have that, 60.2. And then I have to multiply by the sine of 2 alpha. That is the sine of 60. Multiply. And then I think I have to divide by g, that is right, 9.8. And I find 5.31 plus or minus. Now, 2% error in the sine of 2 alpha, 5% error in V0 squared. That gives me, I can't help it, a 7% error. So I have a 7% uncertainty multiplied by 0.07. So I cannot trust this any better than 37 centimeters. And so now I'm going to put the markers out at 5 meters and 31 centimeters. This is the 5 meter mark, 31 centimeters. And I allow for 37 centimeters on either side. It's here. And 37 centimeters on this side, that is here. I'm going to set the angle at 30 degrees. Yeah, waar kom je? We need woman power here. Stay here, stay out of the fire line, and when that ball hits, you jump on it. Yeah, you jump on it. Okay, everything under control. 5, make sure I marked it right. 5 meters 3-1, that looks about okay.